So last time we were doing combinatorial proofs, which was it was a nice idea because it allows us to prove things where sometimes the things we were proving can be proved algebraically, but we were getting these kind of nice combinatorial proofs, which gives you more understanding. So that was kind of the least algebraic uh, lecture, but today is going to be something a bit different in the sense that this is going to be like very algebraic. Okay. So what we're going to do today is something called the binomial theorem. Before we do that, let's do a poll. So how many ways are there to rearrange the letters x, 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 so 7 x's and 5 y's? So what I mean is how many different words can you get by rearranging those letters? So okay. So this is something you should be able to do using the concepts we've done so far. So is the question clear? How many words can I make by just rearranging these 12 letters? We've got some answers coming. Yeah, so these 12 letters, there's 7 x's, there's 5 y's. Okay, so maybe I'll start solving it while we... and feel free to give your answers as I go. Let me see. Yeah. So, okay, here's a way to think of it, right? You can imagine I just write down the numbers 1 up to 12. And so these are kind of 12 different positions for the word, right? And if I'm making a word, I'm going to basically choose 7 of those positions to be x's, right? And the other ones are going to be y's. Or in other words, you can think of it alternatively as choosing 5 of them to be y's and choosing the rest of them to be x's. So for example, I could choose 4, 5, 8, 10, and 12 to be y's, and then the rest are x's. So then it becomes clear that this is so the majority did get this one right. So this is 12 choose 7, right? Because I've got 12 different positions and I'm choosing 7 of them to be x's. But alternatively, it could be 12 choose 5 because obviously, well, as we've seen, those two things are the same. Right, so this is 12 choose 5 or 12 choose 7, either way. Okay, so this is just a bit of review. And this is actually quite relevant to what we're doing today. So the topic today is the binomial theorem. So the thing we're going to learn about today is, suppose I take a polynomial in 2 variables. So I take x plus y. So I take a binomial, x plus y, and I raise that to the power n. And what we want to address here is what are the coefficients of this when you expand it out. So to make this a bit more clear, perhaps, so what I mean is, when you expand completely. And this will have interesting consequences for counting, basically. Okay, let's play with some examples, maybe. Well, I'll start with the easiest ones. So if let's say x plus y is not equal to 0, so that's there's important issues that come up when when you deal with this. So we can't, 0 to the 0 is undefined, right? So it wouldn't make sense for me to write x plus y to the 0 if x plus y could be 0. But if x plus y is any number raised to the 0, right? We all know that that's 1. X plus y to the 1 is just x plus y. X plus y squared, so x squared plus 2xy plus x squared, y squared. So I'm not sure if this is helping much. But okay, what's x plus y cubed? Well, I can't do that in my head, so I write it like this, right? X plus y times x plus y squared. We already kind of expanded x plus y squared. So this is x cubed plus 2x squared y, okay, plus 2xy squared. This must be really riveting watching me do algebra. Yeah, maybe we should. So I won't perhaps do this for much longer. But y squared x plus yx squared plus 2xy squared plus y cubed, right? And then there's some stuff you can collect. That one with that one. And anyway, so the coefficients here end up being, I've probably messed something up here. 1, 2. Yeah, I should have never thought it was a good idea to do algebra on the fly. But if you expand things out properly and collect terms properly, you get that the coefficients are 1, 3, 3, 1. So, okay. And if you kind of are familiar with Pascal's triangle, you'll start seeing that the numbers here look a lot like the numbers you see in Pascal's triangle, right? This is, so 1 here is 3, choose 0. Here we have 3, choose 1. Here we have 3, choose 2. And there we have 3, choose 3. Okay? And this is not a coincidence. So the general binomial theorem says that if we let x and y be real numbers, where we have some conditions because we don't want to take, for example, 0 to the 0 or have any other sort of issues with things being undefined. So we assume that x is not 0, y is not 0, and x plus y is not 0. Although, n is a non-negative integer, so non-negative just means, right, that n is at least 0. You can, in certain cases, I can let, if I assume, you can get rid of some of these conditions in some cases, and we'll see examples of that later. But just for the purposes of this, let's assume all of these conditions. So what we want to say, what the binomial theorem says is that x plus y to the n is the sum of k equals 0 up to n choose k, x to the k, y to the n minus k. Which may not seem, like it has anything to do with counting, but we'll see actually that this is a very valuable result. And so because of this theorem, we often call these numbers, like n choose k things, we call those binomial coefficients because of the binomial theorem, right? Because they are the coefficients you get when you take a binomial and you raise it to the power n. So if I ever say the word binomial coefficient, then what I'm talking about is n choose k for some n and k. Okay, so that's just a bit of terminology that you should remember. Okay, are there any questions about the statement of the theorem? Okay, so what I'll do is I'll give a proof of the theorem, and then we'll look at some applications, which is, the applications are the most important thing for you, but also understanding the proof is quite useful as well. Oh yeah, so this is what I just said. We call these numbers binomial coefficients because they are the coefficients you get when you take a binomial x plus y and you raise it to the power n. Okay, let's I might actually give you two proofs of this, but let's give one inductive proof. So I've just restated the theorem at the top. So this is the same, this is what we just wrote before. Okay, so let's do induction on n. So what about the base case? So here we're dealing now with the case n equals 0, so base case. What is the left-hand side of the equation in the base case? So the left-hand side is, of course, just x plus y to the 0, right? Where, since x plus y is not 0, we can write that this is 1. That's how exponents work. If you take something to the 0, it's 1, unless that thing is 0, and then it becomes a little bit dicey because it's not technically defined. Okay, what's the right-hand side? So the right-hand side is the sum from k equals 0 up to 0, right? Because remember, we're in the case n equals 0 of 0 choose k, x to the k, y to the n minus k. Well, where n is 0, so 0 minus k. So obviously this sum is not really a sum, it just has one term, right? So it's 0 choose 0, x to the 0, y to the 0. Again, using that x and y are not 0, we can, and so 0 choose 0 is 1. You can get that by the formula, for example, right? 0 choose 0 is 0 factorial over 0 factorial, 0 factorial. 0 factorial is 1, right? So this is all equal to 1. And okay, so that proves the base case. So 1 does equal 1, and so we're happy. Okay, any questions about that? Okay, then let's do the general case. Okay, so in the general case, what we're dealing with is x plus y to the power n, right? That's the left-hand side. But we're able to use induction. So, I mean, the good thing about this is that x plus y to the n is the same thing as taking x plus y times x plus y to the n minus 1. And by induction, we know how to deal with this. So by induction, this equals, so that I'm going to keep the x plus y in the front. And then I can write this as the sum k equals 0 up to n minus 1 choose k, sorry, up to n minus 1. n minus 1 choose k, x to the k, y to the n minus 1 minus k. So this equality here, is by induction. Basically, I'm just applying the theorem to the case n minus 1, the n minus 1 case. Is everything clear so far? Are there any questions? Still no questions about math, just questions about the orange shirt I was wearing earlier. The inductive hypothesis. Yeah. So I guess I am kind of, just assuming that everyone's quite familiar with it, or in some sense, I'm assuming you kind of know what I mean by this. But yeah, so in the case for n, our inductive hypothesis is that the theorem holds for n minus 1. But what do I mean by that? So the inductive hypothesis is that x plus y to the n minus 1, which is like the thing, so the statement of the theorem, but applied to n minus 1, equals the sum k equals 0 to n minus 1. N minus 1 choose k, x to the k, and I'm running out of space here. Let's move this over. But yeah, the last thing is y to the n minus 1 minus k. It's basically the thing we're trying to prove, except we plug in n minus 1 in for n. Yeah, so here what we're doing is we're applying the inductive hypothesis by making this substitution, that this equals that. Okay, so now I want to, so actually what we've got here is we've got a product of two different polynomial things, right? We have x plus y times this big sum, right? So we do this, I don't know, at least when I was in high school, they called it FOIL, first outside, inside last. I never really understood what they're talking about. But the thing, the thing where you take some sort of thing, which is a bunch of terms times another thing. What you do is you take the first term here, x, and you multiply that to all the stuff here, add those all up, and then take y and multiply it to everything and add those up, right? That's how multiplying, that's like the, what do you call it? Distributive property or something. Anyway, that's how multiplying stuff works, multiplying and adding. So what do we get then? So when I multiply x to everything, what I end up with is the sum from k equals 0 up to n minus 1 of the same thing, n minus 1 choose k. But now I get x, so I'm going to multiply this x to the k, or I'm going to multiply this thing by an x, so I get an extra x. So it's x to the k plus 1, y to the n minus 1 minus k. Okay, and then from multiplying the y's, I get the sum k equals 0 up to n minus 1, n minus 1 choose k, x to the k, y to the, so I'm going to have an extra y, right? So now I'm computing what happens when I multiply y times the kth term of this sum. So it's just n minus k. Can anyone see what we want to do with this? Well, what I would like to do is apply Pascal's formula, or Pascal's identity, right? So if I look at this sum, I can rewrite it because I can think of it as going from 1 up to n of, so if I take this sum only, what I can do is write it as the sum from k equals 1 up to n. So I'm basically just changing my indices. So basically I'm imagining, I'm sort of replacing k with k plus 1 in some sense. Maybe it's better, instead of using the same number again, using k again, let me just make it a little bit clearer, and I'll just say that, suppose that I equals k plus 1, just to make our lives, I don't want k to be used in too many different ways here. So imagine I write this sum in terms of I. So if k goes from 0 to n, then I goes from 1 to n. Sorry, if k goes from 0 to n minus 1, I goes from 1 to n, because I is 1 more than k. And if I write this, if I kind of do a change of variables, so k is equal to I minus 1, right? If I is k plus 1, then k is I minus 1. So if I substitute here, I get n choose I minus 1, x to the I, y to the n minus I. So this is just substituting k equals I minus 1. Okay. And if I just, I can just write this second sum also in terms of I. But except I'm going to just, so in this sum, when I rewrite it, I'm just going to let I equals k. So I equals 0 up to n, n minus 1. Sorry, that should have been minus 1 here in the first sum. N minus 1 choose I, x to the I, y to the n minus I. now I can combine these things, right? And I can use Pascal's identity. So the only case that you have to think about a little bit more is the case, this should go up to n minus 1, right? The cases I equals 0 and I equals n, right? But if you think about it, so I know that if I take these two things, n minus 1 choose I minus 1, and I add that to this, n minus 1 choose I. Sorry, it's getting a bit cramped here. If I add these two things up, I know that I get n choose I. That's by Pascal. So that's what the poll was on at the beginning. Remember Pascal's identity, n choose I equals n choose I, n minus 1 choose I minus 1 plus n minus 1 choose I. And when I combine all of this up, and you have to maybe think a little bit about the boundary cases when I is equal to 0 or I is equal to n, but if you think about it, it does work. And you get n choose I, x to the I, y to the n minus I. Or sorry, n, yeah. Which is exactly what we wanted, except I've just written in terms of I instead of k, but the name of the index doesn't matter, right? Sorry if that's not too visible at the bottom of the screen. I'll just do that. Maybe you can see it. Is that clear? So this was an algebraic proof using Pascal and induction. Okay. Let's what I can do now is actually think about, instead of thinking about an algebraic proof, let's think about a simpler, in fact, combinatorial proof. Yeah, so there's a question about why I can set I equals k and I equals k plus 1. That's that's really just about so basically if I, in the first sum, like in some sense, if you're summing over, some index I, the name of I doesn't really matter in some sense. So in the first sum, I could, it's basically, the only reason I even define this I is just to like change the index of the sum, right? Just to rewrite the sum in a different form. The second one I didn't really have to rewrite. Okay. It's a bit hard to explain, but if, the I is just the name of the index. It doesn't really matter for the proof. Like, in some sense already, before I did that, this k and this k aren't really the same k in some sense, because they're in two different sums, basically. Yeah, it's still summing the same numbers. That's the key point. The reason I made the i's, I wanted to make the index I in both sums, like I wanted to give it the same name, is so that it was really, so to make it clear that I'm applying Pascal, because n choose I equals n minus 1 choose I minus 1, n minus 1 choose I. If I was writing n minus 1 choose I minus 1 and n minus 1 choose k, I think that would make it even more confusing. So that's the key. And so there's a question about how I combine them in the last step. So that is using Pascal's identity. So n minus 1 choose I is equal to this thing, n minus 1 choose I minus 1 plus n minus 1 choose I. So basically, so here I can, if I can combine these sums, right? So I can take, x to the I, y to the n minus I times, so I can rewrite it as this plus this times that factor. And that plus that is equal to n choose I by Pascal. So this is this slide has gotten really messy now, but sorry about that. So that's how you do the combining. It's using Pascal's identity. Okay. A simpler way to explain this, although, kind of simpleness is in the eye of the beholder, right? Some people really like doing algebraic manipulations, and that works for them. But another way to see it, if you don't like the algebraic proof, is to think about a combinatorial proof. So basically, take n plus y to the n, or sorry, x plus y to the n, and write it out. X plus y times x plus y, all the way up to n. And now think about how it works when you expand a product of polynomials, right? What you do is you take the first, you take the first term, you pick either x or y, right? You take x times, whatever is in the next thing, and then you do y times the other thing, right? So it's like if I have x plus y, a plus b, I pick x and I write down xa plus xb, and then I pick y, and I write down ya plus yb. If you think about it, you can sort of, what's going to end up happening is that, like, basically if I expand all of this, and I suppose you don't collect any terms, right? Before I collect, so if I see, x, y, x, y, for example, and I see x, y, y, x, initially ignore the fact that these are the same, right? Just write out the big, long polynomial. And if you think about it, that polynomial is going to have, before I collect anything, there's going to be 2 to the n terms. And those 2 to the n terms come from saying, for each factor here, for each of the n factors, I choose x or y, right? So there's 2 ways to choose for the first one, 2 ways for the second one, third, fourth, up to the nth one. So there's 2 to the n choices. And basically this corresponds to making a word, kind of, right? If I take, so imagine, so we think about these terms as binary words with the alphabet x and y, right? So for the first one, I have 2 choices, x or y. Second one, I have 2 choices, x or y, and we write out that word. And how many, but then the question is, how many of these words, have k x's? So how many words of length n using an alphabet x and y have k x's? And that's sort of what we were playing with earlier, right? It's just n choose k. So what I'm saying is that there's a one-to-one correspondence between the coefficient of the term x to the k, y to the n minus k, and the binary words, the words with k x's and n minus k y's. So the reason that what I mean by 2 to the n terms is before you combine any terms, if you don't combine anything, then you get 2 to the n terms, because it's the same as the number of binary words, right? Because to make a term in the expansion, what I do is I pick x or y for the first, I pick x or y for the second, I pick x or y for the third up to the nth, and I multiply those things out. So the number of choices is 2 times 2 times 2 by the product rule up to, n time, we have 2 choices, and there's n letters. Okay, so this is a sort of combinatorial proof, right? What we're doing is we're trying to say the coefficient is going to be equal to the number of binary words with k x's, and that's n choose k. So that's, it's perhaps a little bit confusing, but if you think this through, think through that correspondence, it's not actually too terrible. So there you have 2 different proofs of the binomial theorem. Okay, so just to test what we've learned, what is the coefficient of t to the 7, q to the 4 in the expansion of t plus q to the 11? And you also have the option to give me a bit of feedback to tell me to stop doing these polls. So for this, you don't really need to understand the proof of the binomial theorem, right? This is just asking, do you understand the statement of the binomial theorem? So what is the coefficient? And so just applying the binomial theorem, we know that t plus q to the 11. So this is what the binomial theorem says. This is the sum k equals 0 up to 11. T choose k, or sorry, t plus, sorry, no, 11. I must be half asleep. So 11 choose k, t to the k, q to the 11 minus k, right? Because 11 here is playing the role of n. So I've got an 11 here. That means n is equal to 11, right? So the term we're looking for is when k is equal to 7. So it's 11 choose 7. That's the coefficient, right? Because the term with, so it's 11 choose 7, t to the 7, q to the 4, and this is the coefficient. Okay, so that's what we get. So that's what I think most people got, but there might be a little bit of confusion still about this notation, like c n k is n choose k written like this, right? Anyway, okay. Okay, apparently got very into polls for this one. So let's try another thing. So this is a little bit of a, it's a little bit harder. So there's a little bit of a twist in this one. So what is the coefficient of x to the 9, y to the 13 in the expansion of 2x plus y to the 22. Right? So there's a little bit of a trick here, right? Because, I mean, here we've been just looking at the case where you've got, just say x plus y to the n, but there's a 2, right? So what does that 2 do? That's sort of the question here. So the way to kind of understand this most easily, I think, is by doing a substitution. So if I let z equals 2x, then this thing is equal to z plus y to the 22, which is then equal to the sum k equals 0 to 22. 22 choose k, z to the k, y to the n minus, 22 minus k, right? So what we're looking for here is the case k equals not 9, but now we can substitute back in, right? So this is k equals 0 up to 22. 22 choose k, 2 to the k, x to the k, y to the 22 minus k. And so now what we can see is that the coefficient is going to be, so if I look at the case k equals 9, what I get is 22 choose 9, 2 to the 9, and then you get the variables, right? X to the 9, y to the 13, right? So this is my coefficient. Okay, so, right, so those who had, so there was, so 22 choose 9 is most of it. That was the key thing to get from the binomial theorem, but you also have to, it's important here that we're looking for the coefficient of x to the 9, y to the 13, not the coefficient of 2 to the 9, x to the 9, y to the 13, right? So the full coefficient is going to have a 2 to the 9 because there was an extra 2 in the question. Okay, so let me go through another example, which I won't put as a poll this time. So what is the coefficient of x to the 17, y to the 6 in this slightly nasty thing? So x to the 4y minus 3x y squared to the 5. Okay, let's do a substitution. So that's actually a pretty useful trick in all of these things. So let's suppose I let w be x to the 4y, and I let z equal negative 3x y squared. Okay, this is just to make my life a little bit simpler in the beginning, and then we can kind of resubstitute these things back later. Yeah, so the answer is the answer is going to be a coefficient of a term in the summation. Yeah. So when I ask what is the coefficient of something in whatever, that's what I'm asking for. Okay, so the original sum, or the original expression, can be rewritten like this after doing the substitution. So we can now just apply the binomial theorem like usual. K equals 0 to 5, 5 choose k, w to the k, z to the 5 minus k, right? This is applying the binomial theorem with n equals 5. And now we can substitute it back in, right? We can go k equals 0 to 5, 5 choose k. So what are we going to get here? X to the 4k, well, maybe I'll just do it a little slower. So x to the 4y all to the k, and then a negative 3xy squared all to the 5 minus k. Now we remember how exponents work, right? When you take an exponent, you take something to some exponent, and then you put that to another exponent. The exponents multiply. So 5 choose k. So this term here, this factor becomes x to the 4k, y to the k. Okay, so I'm going to use that. And I'm also going to use that this one becomes, so it's negative 3 to the 5 minus k times x to the 5 minus k times y to the 10 minus 2k. Sorry. That might not be too visible, but the exponent on y says 10 minus 2k. And when you have different exponents going on, when you combine them, if you multiply them, you add the exponents, right? So I can put together this. So I've got x to the 4k here and x to the 5 minus k. I can add those exponents and do a similar thing with the y. So I'm going to rewrite this. I'll put the constant first. So negative 3 to the 5 minus k, x to the, so 4k plus 5 minus k is 5, let's say 3k plus 5, and y to the 10 minus k. So is it clear how I did this step? This is mostly just algebra. Okay. But now how do we finish this off? Well, we want the coefficient when of x to the 17, y to the 6. So we have some equations here to deal with in some sense. So let's deal with the y equation because it's a little simpler. But we want the term where, we want to look at the term where k has the property that 10 minus k equals 6, right? Because we want to, here I'm looking at this 6, and I want the exponent on y to be 6. And I know that the exponent on y is 10 minus k. So I want 10 minus k to be 6. So when does that happen? Well, that means that k is 4. And fortunately, when you plug in k equals 4, luckily, you also get a 17 here. So if I plug in k equals 4, what I get is coefficient 5 choose 4, negative 3 to the 1. So that's my final answer. So in other words, it's like negative 15. Okay, this was a little bit more of an involved example. Is it clear? Are there any questions about this? So yeah, these are the types of things I think appear on the assignments and stuff like that. So you should practice with these types of questions. So far we've mainly looked at how to deal with different examples of applications of the binomial theorem in terms of just like computing coefficients. There's some cool stuff you can do with the binomial theorem by just like in terms of proving combinatorial identities. So the whole last lecture on Thursday was about proving combinatorial identities using combinatorial arguments. And the binomial theorem gives you a cool way of proving these things, which is like purely algebraic. So sometimes it's better to use an algebraic proof. Sometimes it's good to use the binomial theorem, and other times it might be better to use a combinatorial proof. Okay, so here's for an example. So like, what if I take the binomial theorem and I just plug in x equals 1 and y equals 1? Right? So what I get is, on the left-hand side, 1 plus 1 is, as we all know, it's equal to 2, hopefully. And then if we look at the right-hand side, when I put x equals 1 and y equals 1, 1 to the k and 1 to the n minus k is just 1. So I just get the sum of binomial coefficients. Okay, so this is one of these identities we've been thinking about. We gave a combinatorial proof last time, and this is perhaps even an easier proof where you just take the binomial theorem and you plug in x equals y equals 1. As another example, plug in x equals 2 and y equals 1, and you get 3 to the n equals, well, so what does it equal? Sum k equals 0 up to n. Remember, I've set x equal to 2, so I get 2 to the k, and then I get 1 to the n minus k, which is just 1. And I think this is one of the things we proved last time too, with a combinatorial proof, right? Looking at ternary strings and stuff. So this can be proved with a nice combinatorial proof, but it can also be proved, once you know the binomial theorem, you can just plug in the numbers. So that's kind of another example. This is a nice one. This is a really nice one. Maybe. Oh no, maybe this is not the one I was thinking of. Plug in x equals 3 and y equals negative 1, right? 2 to the n equals the sum k equals 0 up to n of, so this becomes a kind of wacky, identity. So you can think if you want about how you would prove this combinatorially, but I'm not sure if it does have a good combinatorial proof. It probably does, but it's not obvious, right? So this is what you get. You've got 2 to the n equals sum from k equals 0 up to n choose k. So 3 to the k just comes from plugging in x equals 3, and negative 1 to the n minus k comes from plugging in negative 1 for y. So you have this weird alternating sum, right? Because every term, so the first term, well, depends on the parity of n, but you're going to get negative terms and positive terms adding up with this this power of 3, and somehow, magically, this equals 2 to the n. Okay. Yeah, I actually never thought about this before this lecture, but I have no idea how I would do a combinatorial proof of this, right? What on earth does the right side of this count? I have no idea, but maybe that's a nice thing to think about. Okay, so you can prove some kind of crazy things. Here's another one we have to be a little bit careful about. So when I stated and proved the binomial theorem, we made the assumption that so it's written in this corner. So we made the assumption that x plus y is not 0, but that was only to deal with the case that n equals 0, right? Because we wanted to avoid this 0 to the 0 thing, right? 0 to the 0 is not defined. It turns out if you think about it, so if you do the same proof, for example, the inductive proof starting with n equals 1 instead of n equals 0, then you can actually deal with the case that x plus y is 0. So it is true, the binomial theorem is true for x plus y equals 0 as long as n is at least 1. So that's something to be aware of because that avoids the 0 to the 0 issue. Okay, so if we plug in x equals 1 and y equals negative 1, and we assume that n is at least 1, we can apply the binomial theorem. So what's the left-hand side now? If I put x equals 1 and y equals negative 1. Anybody? So what's the left-hand side? Yep. So easiest thing in the world. I'm just trying to check if everyone's awake here. So it's 0, right? 0 to the n is 0 as long as n is at least 1. Okay, so 0 equals the sum k equals 0 up to n of n choose k, so 1 to the k, which is 1, of course, negative 1 to the n minus k. So this is like this, so if n is, okay, so actually let me switch this around just to make my life a little bit easier. Let's suppose that, so this is the same, it doesn't make a difference, but let's suppose that x is negative 1 and y is positive 1. Okay, so I'm going to change this a little bit just because I don't want to deal with whether n is odd or even. So this would then become the sum k equals 0 up to n of n choose k negative 1 to the k, 1 to the n minus k. Right, and this is just an alternating sum of binomial coefficients. So it's n choose 0 minus n choose 1 plus n choose 2 minus n choose 3, plus minus up to, so it depends on whether n is even or odd, but you either get plus or minus n choose n. And what we're saying is that this equals 0, which is kind of cool, right? This kind of says the number of odd, so if for example, I take the negative terms, I put them to the other side, what this says is that n choose 0 plus n choose 2 plus ... is equal to n choose 1 plus n choose 3 plus ... So the number of odd subsets of 1 up to n equals the number of even subsets. When I say odd, I mean subsets of odd size equals the number of subsets of even size, which is clear in some cases when n is even, but it's not so clear when n is odd. Anyway, so this is a nice identity. This is actually going to come up again, so don't forget this sum, this alternating sum of binomial coefficients, because that's actually going to come up in the chapter on the inclusion-exclusion principle. Okay, any questions about this? So all I'm trying to show you here is that by plugging in numbers to the binomial theorem, you can end up with some kind of interesting identities. So you can also end up with interesting identities by doing some other manipulations, right? By taking derivatives, for example. So do you guys know partial derivatives? I guess probably calculus 3, you may have learned that or something. If you don't know what a partial derivative is, it just means, so this is like taking the derivative. If I do this notation means like take the derivative of x where you treat y as being a constant. So what's the derivative of the left-hand side with the partial derivative with respect to x? Any volunteers? What is, if I take the left-hand side, this thing, what's the partial derivative with respect to x? Okay, so we've got one answer. That is correct by the chain rule, right? So what chain rule says, like, you should kind of take the derivative of the outside thing. So that just means you put n x plus y to the n minus 1. Yeah, and then the derivative of the inside is just 1. So that's like that. What's the derivative of the right-hand side? that's perhaps a bit easier because you don't have to do the chain rule. You just, yeah, so it's k. Basically, you look at the x thing, you treat y as a constant, and then you have this. Oh, but there's one thing I need to be careful of. So what I've written here is actually technically wrong, because there's a little bit of a difference at the case k equals 0, right? Right? Because what's the 0 term here? So when k equals 0, you've got n choose 0, y to the n. So it's a constant with respect to x. So the k equals 0 term actually disappears because the derivative of a constant is just 0. So actually what you get is this, right? The sum from k equals 1 up to n, because the 0 term has partial derivative equal to 0. Now let's say I plug in x equals y equals 1, for example. And then we actually get another one of these identities we proved last time. So I get n 2 to the n minus 1. I think we proved this last time. Sum from k equals 1 to n. N choose k, well, times k. This is kind of like, there's a nice combinatorial proof of this, right? It's like choose a committee that's non-empty and then choose a chairperson, right? But here's another proof using the binomial theorem by taking a derivative. Any questions about that? Okay, let's test our some more calculus. Let's take an integral. So what happens if I integrate from, let's just do a definite integral here, from 0 to 1, x plus y to the n dx. Well, you could do some sort of substitution here, but I think if you think about it, it's not too bad. You don't really need to do a substitution. You can kind of just write it down. So this is x plus y to the n plus 1 over n plus 1, and we're evaluating that at 0 and 1, or yeah, we're doing it from 0 to 1, and that's x equals 0 and x equals 1. So you get 1 plus y to the n plus 1 over n plus 1 minus y to the n plus 1 over n plus 1. Let's suppose we just throw in y equals 1, right? So what we get is 2 to the n plus 1 over n plus 1 minus 1 over n plus 1. And you can integrate the other side. So this is just showing you different ways you can get identities using the binomial theorem. So if you integrate the other side, it's a little bit easier. And we're going to set y equals 1. So if I integrate x to the k, I get x to the k plus 1 over k plus 1. I'm going to evaluate that at 1 and 0. The 0 will just give me 0. So I believe what you get here is just 1 over k plus 1. So this is integrating the right-hand side and setting y equals 1. So what we get is that 2 to the n plus 1 minus 1 over n plus 1 equals the sum k equals 0 up to n, n choose k times 1 over k plus 1, which is a totally weird identity, which you get from the... Hopefully I've done that right, but if not, sorry about that. Okay, let's perhaps not do this. This is what I already said. So it's a committee argument. Choose a non-empty committee, and then choose a chairperson. You can also do that by saying, I'm going to choose the chairperson and choose a non-empty committee from the rest of the... Sorry, choose a possibly empty committee from the rest of them. So that's what you get on the left side. Anyway. Okay, let's, for the rest of the time, so this is going to be something I know for sure you're going to see on your assignments, which is doing more of this practice with the computing coefficients. So let's do another poll. What is the coefficient of x to the 12, y to the 20 in this thing? Okay, so this is one of these harder ones. So like I said before, really the systematic way of doing this is to do a substitution, right? After you get more practice, which I of course recommend you doing, get as much practice as you can with these. Once you get more practice, you might be able to do it a little bit faster without formally writing down the substitution. But for now, I would suggest, until you get used to it, write down a substitution. So the substitution I'll use is w equals 4xy squared, and z equals negative 5x squared y cubed, right? And then we can rewrite this thing as w plus z to the 8, right? The binomial theorem says that this is the sum k equals 0 up to 8. 8 choose k. w to the k, z to the 8 minus k. Okay, so it's basically going to be 8 choose something times something. Okay, so we need to work out what the something is, but yeah. So we do the substitution back, right? So we have 8 choose k. So what I mean is I'm going to plug in. So w is 4xy squared. I'm going to plug that in. So what we get is 4 to the k, x to the k, y to the 2k from the w. And from the z, you get a negative 5 to the 8 minus k, x to the 16 minus k. Sorry, that's getting terrible. I'll just write below it. So x to the 16 minus k, y to the 24 minus k. I collect the exponents. So I've got 4 to the k, negative 5, 8 minus k. Collect the exponents. It's x to the, sorry, that should be 16 minus 2k here. And this should be 24 minus 3k. So 16 minus k, y to the 24 minus k. And now we just have to figure out which value of k are we dealing with here. And it looks like it's k equals 4, right? Because if k equals 4, then the exponent here will be 12, and the exponent here will be 20. And that's what we want. We want a 12 and a 20. So then we get 8 choose 4, 4 to the 4, negative 5 to the 4. And like always, you can simplify this if you want, but you don't have to, right? You can just leave it in this form. Okay, so that is what the majority ended up saying. But yeah, practice makes perfect with these things. So just like everything else in the course, pretty much. Okay, what is the coefficient of x to the 5, y to the 6 in this thing? So x squared y plus x squared y cubed to the 4. So all to the 4. And I gave a little hint. It is indeed a trap. Can anyone tell me the answer? And maybe a justification. So how is this a trap? Yeah, the answer is 0. Why is the answer 0? I mean, there can be lots of possible reasons, but or lots of ways to say the same reason. Yeah, that's the key here. So this is, I mean, don't get stuck on these ones in terms of like, you could go ahead and do the substitution. You can spend time working out the exponents and then get confused. But I would suggest, don't do that. Here you can recognize immediately that you cannot make this term from multiplying things like this and things like this. You just can't do it, right? Because I want a coefficient, or I want the exponent of x to be 5. That's an odd number. No matter what I do, like if I combine x squared y with a bunch of x squared y cubes, like that's what you're going to get when you expand this, right? You're going to get products of several of these with several of those. And no matter what you do, you'll never get an exponent of 5 on the x. So here you can immediately, without even thinking, well, doing just a little bit of thinking, just noticing this, you can write 0. Okay, so I don't think you're going to encounter this very often, but just to be aware, these questions are not always necessarily like answerable by, doing if you did the substitution, you can figure out that there's no solution. Like basically you'll get something where, you have a bunch of things that are like x to the 2k plus 8 minus 2k or something, and then y to the n minus k, so 4 minus k plus 3k or something. Like you'll get, if you do the expansion or you do the substitution and everything, you'll get like that the terms look like this, and then you'll try to solve for k, and you'll get that there's no solution, right? So that's or that you'll get that it's not an integer. So rather than being confused about that, you can just tell right off the bat that this is not going to work. A little bit of foreshadowing. So here we've been looking at things like x plus y to the n, where n is an integer, which is a totally reasonable thing to do. Because why would I really care about x plus y to the 3/2 or something? But that is also interesting, right? So if I take something to a real number, so let's say 1 plus x to the p, where p is a non-zero real number. not necessarily an integer. It's also kind of interesting to think about what's the expansion of this. Also, it's interesting to think, what do I even mean by expansion? But that's something that actually we're going to do later in the course. So that's just a bit of an advertisement for something coming later. And maybe I'll do another kind of foreshadowing here. So another way you could extend what we've done today is to look at not just binomials, but trinomials. Right? If I take x plus y plus z to the n, it's natural to think, what's the expansion of that, right? It's going to be a bunch of things that are like, it's going to be a sum where you've got something here times x to the a, y to the b, z to the c, right? Where a plus b plus c is equal to n. But it's interesting to ask, like, what is the coefficient here? So that's going to be the topic of the next lecture. Okay, so understanding, and then more generally, we can look at four terms, x plus y plus z plus w to the n, and so on. Okay, so that's what we're going to focus on next time. A lot of the same ideas that we looked at today will be applied again next time. But yeah, so maybe I'll end this class here. Do we have any questions though before we go?